Thanks. Can you hear me? Yeah. Cool. So I'll hit start. Okay. So I'm Rodolphe Lepigre, and I'm going to talk about prophecy variables and how they can be integrated into modern forms of whole logic. And as you can see, this is joint work with many fine people. So I'm guessing that most of you have never heard about prophecy variables before. So I'm going to start by giving an example to give you a feel of what they are and what they can be used for. So the example I'm going to show is a simple coin interface with three operations. So you have coin creation, reading, and tossing. So what happens when you create a coin? Well, first there is a puff of smoke, and then when the smoke dissipates, a fresh new coin appears. And then when you have a coin, you might want to read its value. So to do that, you need to use a magnifying glass because, well, coins are really hard to read. But using it, you can actually reveal the mood of the coin. So either it's in a bad mood or it's in a good mood. And finally, the last coin operation, which is indeed the most entertaining one for coins, is tossing. And as you all guessed it, tossing a coin can affect its value, its mood, in a non-deterministic way. So all of these three operations can be implemented in a straightforward way. So what I've done here is, represent the coin as a record with a single field val that contains a reference to Boolean. And so to implement getCoin, what you do is you simply dereference that pointer to get the Boolean. And for tossing, you update its value with a new freshly picked Boolean. Okay, so now that I've shown you the code, we might wonder what kind of spec can we actually prove for coins. And the first thing we need to define for that is an abstract predicate that actually tells us what the value of the coin is and what are the involved resources. So this coin predicate has two arguments. The first one is the coin itself, and the second one is a Boolean that is going to be true if the coin is in a good mood and false otherwise. And then with such an abstract predicate in hand, we can start giving whole triples for our operations. So for new coin, we don't have any particular precondition, and the operation produces a value C that should be a coin according to our abstract predicate. And so notice that in the postcondition, we actually have an existential quantifier, and this has to do with the fact that, well, at the beginning, we don't know in what mood the coin may be. For tossing, it is required that the argument of the function is a coin, so this appears as precondition. And in the postcondition, it is similar to what happened in new coin, because after tossing, of course, we don't know what the mood of the coin is. And finally, for getting the value of the coin, well, again, we need the input to be a coin. So this appears as precondition, and the function actually returns a value v that should match the abstract value of the coin that appears in the abstract predicate. And also notice that the coin predicate is left unchanged in the postcondition because, well, getting the value of a coin doesn't change its value. So now, what if we want to prove that specification for our coin implementation? And it's actually very easy. So we do the obvious thing, and we define the coin abstract predicate using the points to connective of separation logic. And what it says is that, well, coin CB has exclusive ownership of some location stored in the val field of the record, and that location currently stores the value B. And with that definition, then you can prove the spec very easily. And that's not very surprising because this spec is completely boring. So now let us try to come up with a more exciting spec. So one thing that would be pretty neat would be to have a clairvoyant specification. That is a specification whose abstract predicate can predict upfront all the values that the coin will ever have in the future. And so that the abstract predicate would look like this. So it's pretty similar to what we had before, except that now we have a third argument that is a list of Booleans, and these are the future values of the coin. And of course, to be able to define such an abstract predicate, we'll need to use a kind of crystal ball to be able to predict what is going to happen in the execution of the program later on. But yeah, assuming we can do that, then we can again give a hostile spec for our operations. And here it is, what we have is pretty similar to what we had for the previous example. There are only a couple of key differences. So the first one is that in the postcondition of new coin, we now have a second existential quantifier that ranges over all the future values that the coin will have. And so this really means that once you've created a coin, you really know what all the future values of the coin are going to be. And accordingly, in TossCoin, now we don't have any existential quantifier anymore because, well, all the values are already known. They're stored in the list L, so we just need to access the value. A note here also that in the postcondition, we implicitly learn that the list L could not have been empty because it should have a head and a tail. Okay, so I hope you agree that this specification is a lot cooler. So it's very cool indeed, but is it useful? And it turns out that, yes, it is very useful for proving linearizability in whole logic. So if you've never heard about linearizability before, don't worry. All you need to know for this talk is that it's a standard form of spec for concurrent data structures. And what it roughly says is that every operation on the data structure should appear to take effect atomically. And so one common way of proving linearizability is to identify the linearization point of operations. Because you need to perform some logical update at this linearization point, not before, not after, exactly at the linearization point. So imagine you have some operations that run concurrently in the data structure. So each color here represents one operation. Then for each of them, you need to be able to identify the precise moment where the operation takes effect, appears to take effect from the outside world. And these points are the linearization point. But it turns out that identifying the linearization point is not always easy, because there are some very tricky data structures whose linearization point cannot be identified with certainty. So you might end up in a situation where you're at some program step A, and you wonder, well, is A the linearization point? And the answer to that question might be, well, actually, we won't know before we reach some further step B in the execution. But that's unfortunate, because at A, we really need to know whether we are at the linearization point or not, because we need to perform some action if we are and do nothing if we're not. And so this kind of situation is known as having a future-dependent linearization point. And so I guess you can see how being able to know the future could help here. Okay, so what we really need is for a way for the proof of a specification to know the future. And it turns out that there is already a known and already quite old technique for that, called prophecy variables, due to Abadi and Lamport. Although prophecy variables are still quite exotic, they've been introduced as the dual of history variables, which are more well known. And indeed, history variables are used to record what has happened in the execution of a program so far, while prophecy variables are used to know in advance what's going to happen later. So now, if you look at whole logic, history variables are actually used all over the place. And there's a lot of work on that, and you might have heard of them in terms of ghost state or auxiliary variables. However, prophecy variables have almost never been combined with whole logic before. So if we look at the intersection of whole logic and prophecy variables, there are actually only two pieces of prior work that we are aware of. So the first of them is actually the PhD thesis of Victor Vafagades, and Victor was actually the first to use prophecies in separation logic, and he used them precisely for proving linearizability of these tricky data structures that have a future-dependent linearization point. And so he applied this technique to exactly one case study, which is the RDCSS data structures of Harris et al. And his proof is actually not very formal. It's just it's kind of a sketch, and he's not very precise about how to formalize prophecy variables into whole logic. It doesn't give a general framework. So later on, Zhang et al. Tried to formalize prophecy variables, tried to give a more formal presentation of prophecy variables, but to simplify the problem, they only looked at a special case called structural prophecy variables. And the intuition is that structural prophecy variables only allow a thread to predict the actions, its own future actions, not the future actions of some other thread. However, the author argued that this is okay, it's already quite general enough because, an example like RDCSS can already be carried out because it follows the structural discipline. Sorry. And so you might wonder, well, isn't the problem solved? And actually it isn't, because it turns out we found a flaw in Victor's proof of RDCSS. And so we talked to him, he confirmed it, so the proof is really broken. And it seems that this proof cannot be fixed by sticking to the structural discipline. So we really need to have a more general framework for prophecy variables and to actually have a formal presentation of that. So that's exactly what we've been doing. So in one sentence, what we've done in this work is give the first formal integration of general prophecy variables into whole logic. So here what we mean by general is that we're not limited to the structural discipline. That means that a thread can actually predict the future behavior of some other thread. And what we mean by formal is that we've carried out this work inside the Iris framework for concurrent separation logic, and so everything has been formalized in the Coq proof assistant. And also one advantage of using Iris is that we actually rely on separation logic to prove the soundness of the approach. So that's also an important point. And so we've used this framework then to prove linearizability for a number of concurrent data structures that have a future dependent linearization point. And in particular, we've looked at the RDSS case study, and we have actually found a way to fix the proof. But our fixed proof actually makes essential use of the fact that we have general non-structural prophecy variables. So I'm not going to talk about RDSS anymore, because it's quite complicated, and I don't have time today. So I'm going to try to illustrate the principle of our work using the coin examples that I presented earlier. And I'm going to try to give you a feel of how we can prove our very cool specification. So let's dive in. So remember I told you that we need to use a kind of crystal ball. So why not just introduce that as a primitive to the language? So we do exactly that, and we introduce a new operation called newprof that creates a prophecy variable, and it really corresponds to our crystal ball. Now, we have a crystal ball, but we still haven't asked any question yet. So what is it we want to predict? And in fact, this has to do with the tossing operation. What we want to predict is precisely the value of this Boolean B in toss coin. And so one intuition for how our prophecy variables work is that a prophecy variable can be seen as a kind of communication channel, and what the prophecy predicts is the values that are going to be written to that channel. So we need to, in Toscoin, to have access to the prophecy variable P. So to do that, we actually store the prophecy variable into the record along with the reference. And so in Toscoin, we can then write to the B to the channel using the special resolve operation. And by doing that, what we've actually done is give meaning to a prophecy. So now it actually predicts what we wanted to predict. Okay, so what I've shown you here is that for using prophecy variables with our approach, we need to use ghost to modify the code. And this code is actually ghost code. So what that means is that it does not really modify the computational behavior of the program. So morally, the program we're reasoning about is still the same. Okay, so now let's see prophecies in action. I'm going to do that by showing you a proof outline of what happens when we reason with prophecies. So the first thing we do here is create a new prophecy variable. So what happens there is that we get ownership of a prophecy assertion, prof PL, that relates the prophecy P to its future resolutions, L. And so this assertion really corresponds to our crystal ball. And note that L here is existentially quantified because our proof should work for any possible prediction. So now, for simplifying things a bit, I'll just assume that L starts with two elements, E1 and E2. And so let's see what happens when we resolve. So when we resolve, two things happen. So the first one is that we actually learn what the prophecy must have been. So you can see that we've resolved to B1, and in the prophecy assertion that we had, the first prediction is E1. So we've now learned that E1 and B1 are the same thing. And the second thing that happens is that since we've made an observation, there is one less thing to predict. So the first element of the prophecy assertion actually disappears. And then for subsequent resolutions, the same thing happens. So we learn a new equality, and again, we lose one element in our prophecy assertion. Okay. So the manipulation of prophecy variables that I've just shown you actually makes essential use of separation logic. And actually, the prophecy assertion is really similar to the points to assertion of separation logic. And following that analogy, when you resolve, what you actually do is a kind of mutation of ghost state for people that know what I'm talking about. Yeah. And one last thing, so the code I showed you on the right actually executes in a single thread. So it's not making use of the fact that we support non-structural prophecy variables. But nothing prevents us from transferring ownership of the prophecy assertion from one thread to another thread, and that second thread could then resolve the prophecy. So that's how we support non-structural prophecy in that work. Okay, so now some of you might be a bit puzzled, and you might wonder, as did our reviewer too, what if we have a prophecy assertion that predicts true, and we actually resolve to false? And that's a very good question because, well, won't we get a contradiction in that case? And it turns out that, yes, we will get a contradiction, but that's perfectly fine. Because if you look at the precondition here, what it says is, well, P will be resolved to true. And since that's not the case, then our precondition is false. And so this whole triple is vacuously true. And one important remark is that the only way you can end up with an explicit value like true here in the precondition is for your proof to look like that globally. So remember, when you create a new prophecy variable, you get an existentially quantified list. And so the only way to make progress is actually to reason by case on that value. So it's not surprising that some branches will be inconsistent with the prediction. But what's nice is that some other branches will be consistent with it. So that's how things are not contradictory. Okay, so right. So now I'm going to quickly show you the actual rules for reasoning about prophecy variables. So here are the two rules. So the first one we've pretty much already seen. And the second rule, the rules for resolve, you can see that it requires as a precondition to get ownership of the prophecy assertion. And in the postcondition, it gives back the prophecy assertion, but with one less element. And here, again, as for the coin thing I told you about earlier, implicitly, we learned that the list could not have been empty because it should have a tail and a head. And we also learned that the first prediction came true with this equality between the head of the list and the Boolean B we resolved with. And so using these rules, proving our specification for coins is actually very easy. What you do is you define the coin assertion this way, and then everything comes together very nicely. Okay. So to conclude, I'm just going to flash a couple of things that I didn't have time to talk about. So the main one is logical atomicity in the style of Iris. So logical atomicity is it's kind of similar to linearizability, but it's more well fitted for whole logic. And we actually proved logical atomicity for a number of data structures. And yeah, I think I'm going to stop there because I'm out of time. Thank you.
Excellent. Questions, John?
Thanks, Rodolphe. That was wonderful. I was wondering if there's any interesting interaction between prophecy variables and total correctness or like non-termination. Like, I was wondering if there could be some situation where I could like make a prophecy about like something's going to happen, but then you get sort of non-termination, and so I guess I'm.
So in our work, we're only interested about partial correctness, so I can't really answer that question, at least not in our framework. Yep.
Any more questions? Okay, so you mentioned a few other case studies. Could you be a bit more explicit? What other examples have you done using prophecy variables?
So in Iris, we've considered mainly RDCSS and the Hurley-Wing queues. Mm-hmm. So both of these data structures require have a future dependent linearization point. The techniques are quite different and it's quite complicated, so I can't really explain much of what mm-hmm. happens here.
I see.
Yeah, I don't know what else I can say. So we have a couple of other case studies actually done in very fast. Right. So we've actually axiomatized our prophecy variable interface into very fast so that we can actually develop other examples in that system. So there are like 3 or 4 other examples.
Right. And you mentioned you have mechanized all of this, and you also had this Iris framework of Robert Krebs and everyone for Iris support inside Coq. Did you have to adjust that in any sense, or to be able to use rules like resolve or?
Pretty much everything was already there.
I see.
Well, we actually rely on the fact that in the model of whole triples, we have access to the full execution trace mm-hmm. from the very beginning, which means that we can actually make an accurate prediction. So that's why our prophecy assertion actually makes an accurate prophecy. So, but all of the structure of the proof was already had already this shape. We just remarked that it was possible to extend it for that kind of reason.
So using the standard iris trick of everything can be derived from the base logic, you just use the base logic. So, do we have any other questions from the audience? We don't have any more questions on the slide, though, I don't think, but this is your last chance. Yeah. Well, we have another question from Haman in back. Could you get him? Well, I'll...
Hi, nice talk, Rodolphe. Can you say a little bit about the linearizability in those algorithms? How, if you have it as a spec, how you formalize linearizability in?
So we don't actually formalize linearizability. What we formalize is logical atomicity, which is a closed relative of linearizability, and it's actually more natural when you're doing whole logic. So basically, what this gives us is a standard-looking or-style specification, but you're actually allowed to use the invariant rule around expressions that are not atomic. So yeah, that's basically how that works.
We had one more question.
Is there an interesting connection between these prophecies that you're making and the promises in the promising semantics that also appear in this part of the world?
So I'm not familiar with the promising semantics, so sorry. I'm sorry, I can't answer your question.
It's a bad question.
Oh.
Thank you. Hi.